announcements here, so I'll jump right into it. Let's see, did we do Calc 2? No, I think we did. Yeah, I think we usually end on Calc. You can check. Oops. You can see I had some answers here for calculus from last week. This was Friday's. So today we're doing Calc 2 through abstract algebra. This abstract algebra has only been up for like 8 hours or so, but I'll do it anyway. Let's see. So Calc 2. Yeah, I'm a bit rusty. So it might take me a second to do this one. So first of all, just broadly, there's a couple things you gotta know. The derivative of tan is secant squared. And didn't need the dx there probably. The derivative of secant is secant tan. And secant, of course, being defined as 1 over cos. Tangent is sine over cos. So stuff to know. Oh, yeah, right. Before I seal that off, you probably also want to know some identities, like, you know, probably sine squared, cosine squared, plus sine squared. Excuse me. I don't know if you could hear me at all. Probably cosine squared plus sine squared is 1. Tangent squared plus 1 is secant squared. Yeah. Because this is sine squared over cosine squared. So if you add cosine squared over cosine squared, you get 1 in the numerator. You get 1 divided by a denominator of cosine squared. So and then what else? And then just generally in trig subland, sometimes you have like boundaries here, especially sometimes you make a triangle, you know. That's not what we're doing here today, but for instance, if it was a like integral of 1 plus x squared type of question, something that involved that, it would be kind of clear that you want to use x equal to tangent, but then you would figure out that is in a triangle. Like you'd probably write x for this side leg and 1 for the bottom leg to get x as tangent of this angle. But I'm just daydreaming. I'm sure we'll have a problem like that in the next few weeks since we've started to hit tangent or trig integration. So yeah, this one. This might actually take a minute. So like if it was just secant squared, I would know what that is because it's the antiderivative is tangent. So my instinct is to maybe, because I can see that like sine over cos, I don't think that's going to work because there's like a bunch of factors of sine upstairs. So I can't just do a u substitution. So my instinct is to do something like this. And then use an identity to like split it up and then get, well, yeah, I no longer have secant squared. Well, I have 1, and then I have tangent squared times it. But also this is being squared, so I actually end up with 3 terms. So yeah, what I'm saying, my instinct is to do something like this. This is now tangent squared plus 1, but plus 1, or, squared, excuse me. Tangent squared plus 1 squared. So I end up with tangent to the fourth plus 2 tan plus 1. Tangent secant squared. It's funny, I probably did this like a week ago, but I don't recall. I'm also hesitant because I'm wondering if there's like a smoother way to do this. But anyway, we'll poke at it, see if I did it wrong already. So we're looking at tangent to the fourth plus 2 tangent squared plus 1. Now the 1 is handled. The antiderivative of secant squared, is tangent. The other two are a little gory. If this was odd, we could just do a u sub with secant times tan, but it's not gonna work out for us. And this is also squared. Well, anyway. Yeah, as you can see, I'm a little rusty. Because, like, when you know Calc 2 a little better, well, like you've just taken it or whatever, there's a bunch of these. You basically just memorize a handful of examples, like even powers and odd powers, and usually goes a little smoother. So what I was muttering before is I can't really let u be secant tan. Although, you know what I could do here? This is just a u substitution. If you take tangent, the derivative is secant squared. So I'm looking at a multiple of the derivative just sitting right there. So that's going to work out. This one, of course, is obvious. This one just equals tangent. So the only one I'm thinking about now is this. Is it another u sub? Is it really that easy? This is u to the 4 times its derivative. Yeah, another u sub. All right. Not bad. So what I'm claiming here is the derivative is secant squared. So that's why it was good to like boil it down to leaving a secant squared there and then see how it shook out. And this one, the answer just is tangent on this last one. You don't have to do a u sub. It just, we just know that when you differentiate tangent, you get secant squared. So on this one, it's the same as integrating u to the 4 du. You know, the du replaces secant squared dx, but we've got a power of, 4. This one is more like 2 u to the 2. So tangent is being squared, but there's its derivative. And this last one, the antiderivative is already just tangent, plus some constant. So yeah, we're just about done. I got a fifth. Yeah, u to the 5th plus 2 thirds u cubed. So I believe that's my answer. And I guess we could check our work. I'm a little concerned. Like, of course, here we get secant squared. I don't know really what work there is to check. It either works or it doesn't. But, does it give you secant 6? It doesn't give you secant squared. This one, of course, gives you tangent squared times secant squared. So you get a factor of secant squared for all of them. And then you get tangent to the 4th plus 2 tangent squared plus 1. You get that. So yeah, it's correct. This factor is to be that, which when you square it is the same as, anyway, that's secant to the secant squared squared. So yeah, it worked out. Okay. That's a Calc 2 problem. We can move on. That was 34. Let's look at this multivariable guy. Given two vectors, A and B, A is 3, 1, B is 1, 4. Take the dot product and tell me the angle between them. So what you would need to know is that when you dot two vectors, it gives you the magnitude, product of the magnitudes times cosine. It's a measure of how similar the vectors are. So if they were parallel, if they were moving in exactly the same direction, your angle would be 0, and you just get the magnitude back. That's like the largest it can be, because it's this bounded, like it's this bound times something that's less than or equal to 1. And if they're like perpendicular to each other, this dot product will be 0. So it's a pretty convenient quantity. The other formula for it is the sum of the products of the coordinates. So it's like 3 times 1 plus 3 times 1 plus 1 times 4. So we're getting 7 here as the actual dot product. But another thing you might want to know is the magnitudes, because part 2 of this is asking what's the angle between them. So at this point I can say cosine is A dot B over the magnitudes, like that. And we know the numerator is 7. So we also just need to know what are these magnitudes. The magnitude of A is, well, the square root of the x coordinate squared plus the y coordinate squared. So we're getting 9 plus 1 is root 10. For B, 1 squared plus 4 squared. So 16 plus 1 is like root 17. So that's what's going downstairs is a root 170. Cos theta is 7 over root 170. You could kind of leave it there, or you could also write this as 7 root 170 over 170. You could probably factor this a bit if you wanted to. But I don't know. It doesn't really do a whole lot, right? It's a lot of primes here. I think 17 by 10. So you can't really clean this square root up. It's just 2 times 5 times 17, I believe. But what you could do is actually take, like, the angle is going to be arc cosine or inverse cosine of whatever this real number is. So let's see if I can handle that. Like, you could take 7 divided by the square root of 170. I'm getting 0.53. And then I'm in degrees here, but that's okay. We'll go with that. Inverse cosine of that is 57.5. 57.53 degrees. So I believe that is what I'm going to say for my multivariable part. Differential equations question this week is use Euler's method to approximate 4 points. So points like y1 through y4 with solution in the interval 0 to 1 for this differential equation. So this is a pretty straightforward one if you know, you just have to know what Euler's method is. Euler's method, the idea is that you could even do this in larger dimensions, but obviously here in one dimension, the idea is that we're going to cut this interval that you're interested in, the region that you want to sort of approximate your solution, into equal steps. So here we wanted, it literally tells you the step size. But I suppose you could also come up with a step size if you knew you wanted to use like 6 points or something over length 0 to 3 or something. Anyway, so here's sort of a natural step size. If you wanted to take 4 steps forward, would be 0 to 1 would be 4 steps of size 1/4. So that's what I did with the step size being 1/4. But anyway, the idea is we cut this up, and then there's different things you could do, but with Euler's method, the first time you see it, the first version, you take the derivative at this location and then use your initial value, in our case, y of 0 equals 1. So we're assuming a particular solution. We're going to say that this solution passes through 0, 1. And then they gave us a formula that we'll call f. F of ty, okay, is dy dt. It's like some derivative that depends on potentially both t and y, most likely. Or you would have just solved it exactly if it didn't depend on one of the variables. Or not. No, or not. I don't know. It could be nasty to solve regardless. But anyway, so you're given some function that you can use to get the slopes. And so at 0, I know the slope, and I know a starting point. So like the idea on this would be, okay, we start at 1, and then I'm going to compute what the slope is at that moment. And then I'll just draw something of that slope for that first interval. And then we keep repeating this. So at 1/4, at t equals to 1/4, right? We'll evaluate what the slope there is again, and we'll take our previous starting point, which is no longer 1, most likely. But we'll take our point, and we'll add slope times 1/4 again. So every step of the way, we have a formula like the next position, the next height is given by your current height plus a derivative. Should be a little careful what I write here. Times whatever your step size is. So you're splitting into subintervals, and then you're using a derivative on that subinterval to estimate where we're going to go. Natural questions people would have is like, well, like what's so special about the left side's derivative? I mean, yeah, you know right at that moment that that's where the derivative is, but as soon as you move forward a little bit, the derivative is changed. Or another comment would be like, why don't I use right hand? You know, if this is accurate for this interval, isn't it also accurate going backwards? If I take a step backwards, would I use the same slope, or should I? No, I should use the left-hand side slope. According to this formula, I mean, according to this first pass of Euler's method, we would be using left endpoints, but there's nothing, sacred about that. You could also use right endpoints and do like sort of a backwards estimate. It wouldn't be wrong. It would just be a different method. You could also use like midpoints and some sort of, I mean, I don't know. You could use all sorts of things that, as long as they involve derivatives. Anyway, I'm getting a little crazy here. Later on, you'll see 1 or 2 other approximation methods. This is a good one, though, for the time being. So what to say? So I guess if we want to make quick work of this, I mean, you can see that then if you were using different methods, your formula doesn't change a whole lot. You could just, I mean, I guess it depends on what the method is, but we could use Tn plus 1 here. Um, and that would put you like over here. You know, so the formula would be the same if you're using the left or the right hand endpoint. It's just that you would use a different t value in your slope formula. But anyway, um, let's just compute a handful of these. Oh, I can't do them. I was going to try to do them all at once, but I can't because I don't know what the y value is at each particular moment. So we do have to go sort of successively. So on the first one, to compute like y1, we're going to say it's y0, which we called 1, plus some slope. So now it would be nice if I actually wrote it down, right? F of times 0, t0 and y0 is 0, comma 1. And if I plug 0 for t and 1 for y, you're getting a 1. So our first slope happens to be 1. And then we put the step size here, which for us is always going to be 1/4. So I'm getting 1 plus 1/4, 1.25. So we've gone from a height of 1 up to 1.25. Now in your second iteration of this process, you're just doing this formula again. This 0.25 does not change, but both your, the constant, the constant term, your previous height is different, and your slope is most likely different as well. So we're gonna have a slope here. I don't know why I didn't just put all the numbers in, because we know this is 1.25, but 1.25 plus something. So now we've moved on to a new t value and a new y value, right? T is 1/4 because we've taken one step forward. I could just put it in 1/4. And the y value is not 1 anymore. It's supposed to be y1. y1 is 1.25. So I'm getting these sort of nastier numbers. That's 1/4 squared plus 1.25. 1/4 squared is a 16th. 1.25 is like 5/4. So if you want to add those, you're getting, let's see, 5 times 4 is 20, so 21 over 16. This is 21 sixteenths. You like how I'm mixing fractions and decimals? 21 sixteenths times 1/4 is 21 64ths. So this times 16 is like 80, I want to say. 5 times 16, I'm saying. 6 times 5 is 30. So 5 times 16 is 80. 80 over 64 plus 21 over 64. 101 over 64 is what I'm getting for y2. Yeah, I'm being a bit ridiculous with this. 101 over 64 is 1.578. So we've gone up another like quarter step to right about here, I guess. That's going to be my 1.578. Actually, it's a nice rational number, isn't it? Right. And then I don't know if using this again and again is going to help us. I'm not about to start squaring 64 and stuff, but you get the idea. Y3 is this old value plus a slope, which I haven't computed yet for some reason. Let's get on that. So our old t value, well, our old t value now is half instead of 1/4. So 0.5, and the old y value is this one, 1.578125. So we're going to square this, and we're going to add y, just because that was, you can't see it anymore, that was our formula. T squared plus y. I hope I wrote it down right. T squared plus y. So if I take this number, that's our y, and I add 0.5 squared equals, I get 1.828125. 1.828125. And that's what's going in here in the slope. 828125. That times the slope of a quarter. That times a quarter, and add to it the previous y value that we had just found, y3, or y2, excuse me. 578.125. Boop. 2.035. And it continues, but you don't need to be that precise. That's our y3 is at 2, so we've gone from 1 up to 2. I maybe screwed up my scale a little bit there. And then we want to take one last step, the fourth step. So y4 is this previous value that we found, 2.035, plus a slope. Slope is what? We're going to plug in t3 and y3. y3 was this 2.035 business. T squared plus y is our formula for the derivative. So that's what the slope is. So if I add to this 0.75 squared, I'll get 2.6-ish. 598, say. Getting a little, finally starting to round at the end here, ignoring significant figures. But 2.598 is my slope for T3, Y3, right? Multiply by a quarter. So take this, multiply by a quarter, and add it to your previous value, which I probably could have saved in the calculator if I was trying to like not round at all. But we're getting 2.68. 2.68, about 5 actually, right? So it goes up by 0.6 this time, 0.65. It jumps up in this thing again. I realize this just looks like a straight line. It's not really. So of course, if you wanted a nicer image of this, you would use a computer and you would use a smaller step size. Like even a tenth would be nice, and it would you could maybe connect these dots if you want, and you'd start to get a piecewise linear, of course, approximation to your solution. All right. So the 4 points are, of course, these 4 heights that I just computed: y1, y2, y3, y4. And that is 36. Take a look at 37. Find an LU factorization. All right, the idea on LU factorization, let's call this guy M, I suppose. It's kind of in the name. There's a couple ways to do it. So here's my original matrix. We're trying to reproduce this. We're trying to come up with 2 matrices which when multiplied give you back M, but also the structure of L has zeros in the top, on the top right. You know, and we find these numbers. And then the structure of U is sort of the opposite. This can have, it doesn't have to have ones along the diagonal, just some sort of zeros in the bottom left is the point. So we have an upper triangular you don't have to like reduce this necessarily. Um, but you do but when I said put it in an echelon form, this is what I meant. You know, it doesn't necessarily have to be row reduced. Like there's a one in the leading term. And these guys, we don't really have any conditions. Now, there's a slick way to do it, which is what I'm going to do. Um, huh. Now that I'm looking at this, don't I want this to be a 1? Yeah, these need to be 1s. I think I made a mistake here. Uh, because obviously you can see this wipes out my this wipes out my top row. There's no way that you'll reproduce M. So you need at least 1s on the diagonals. Oops. So yeah, let's assume that there's 1s along the diagonals, right? Then find these numbers. So you could just literally sit down and say like, okay, this is x, y, z, and these are also variables I'm going to solve for, like a, b, c, d, e, f, and you could just jot down the product. You'd have a big system of, I mean, probably 9 equations, right? But you could do it that way. But what I'm going to do, I think, is start reducing m to make it look like this form. So we're just going to do some sort of row operation. We'll do it succinctly in one step to annihilate this -3 and this 9 and then this -5, okay? So we're going to first start in the first column, make those zeros by some sort of row operation. And as you do that, I'm basically going to record what I did on each of these cells. And the reason, you'll probably see right on the first step why that works. So my first step, I'm going to say we just add row 1 to row 2, right? The 3's will cancel. We're going to keep row 3. So like my first step is we're going to leave row 1 alone. In fact, I'm going to leave row 3 alone as well for the moment. But if I add this first row to the second row that we had, it will eliminate this first cell. So what I'm doing is 1 times row 1 plus row 2. If we do like row 1 plus row 2 is the operation that I'm doing to get this. So if we did -1 plus -2, you'd get -3, right? If we do 2 plus 10, we get 12. Now what I'm going to do, my L has 1s along the diagonal, 0s up here, right? But anyway, we altered this second row. What we did was we added 1, right? So my instinct for some reason is to put -1 here. Yep, that's going to be correct. Now watch what happens when if you took this row and multiplied it by this matrix, it reproduces, it basically undoes the work that we just did. If you take -1 times this first row plus 1 times the second row plus nothing from the third row, it'll give you -3 and -2 and 10, which is exactly what we had, right? So I'm putting sort of the opposite of what I just did as an operation. We did like 1 times that first row and we added it to here, I'm saying, right, -1 there because that's the multiple that you added. So yeah, that's it. Do row operations where you're taking a multiple of row 1 and using it to cancel out, and then write down the negative of that multiple in each cell. Well, so for this one, we're going to end up using, I guess, the second row, right? But it's still the same concept. You're using this as like a pivot point of sorts. So right now we're using the top left as a sort of pivot point, but maybe I shouldn't call it that. Usually when you pivot, I think you reduce down to 1. But anyway, that was step 1. Step 2. I can actually see already, but we'll do it first. The operation I'm going to do to M to make it look more like U is to go, let's see, if I double row 1 and then I'm subtracting, right? So if we do like -2 times row 1 and I add it to row 3, this is the second step now. If I, oops, not 2, I'm sorry, 3 is what I meant to say. I guess I was squaring it in my head. If I do -3 times this, basically just this minus that 3 times, right? -3 times this is -9, so it's going to produce 0, of course. That's the whole point. We don't alter the first row. We took care of row 2 already, so don't touch that again. Anyway, so we're changing row 3 by subtracting 3 row 1 from it. So 9 minus 9 is 0. -5 minus -1. This number is not -1, excuse me. This is the computation that I'm doing in my head. -5 minus 3 of these. So -5 plus 3 is like -2. And then 6 minus 3 of these. 6 minus 6. That last step was like -3 of the first row plus the third row. Anyway, happens to give you 0, coincidentally. And what did we just do? -3 times the first row. So in a sense, this is 3 of those. I'm going to put a 3 in my bottom. And this right now is a 0, but we don't. The whole point is we're supposed to be changing these 3 numbers, so that's why I'm leaving it blank. So right now, like if you multiplied this by this matrix, it should still give you back M. So you can see how we're producing a pair of LU. This is going to be U. It just isn't yet. In fact, we can call it U. This is U. Because each time I do this, it's not fully formed yet. It's not in the right format yet. It will be now. But so yeah, apparently you can make an LU factorization in let's see. If it was a 4x4, what do we get? Right? If it was a 2x2, you get 1, then you get 3. So I'm expecting, 1, 2, 3. So I'm expecting 6 steps for the next. It's like the sum of these triangle numbers or something. 1 plus 2 plus 3. Anyway, so we needed 3 spots filled in, or 3 cells annihilated in the bottom left of M, and that's why it's taking that many steps. So we should be done now after this last step. And we'll check it to see if I screwed it up. But my U should be finally in the right form. So we're not going to change row 1. I guess we never change row 1. We're not going to change row 2 anymore. But we are going to use row 2 to annihilate the cell in the middle below it. And these 2 cells might change, right? So normally I would divide by well, negative 3. Normally I would divide by negative 3, I suppose, to make this a 1, right? If I did that, if I divided by negative 3, it gives us 0, 1, and looks like negative 4. So the row operation I'm going to do is divide by negative 3, because this becomes a 1, and then add 2 times. So we're basically doing negative 2/3 of row 2, add that to row 3, right? That's the kind of step that will kill off that. If I took 2/3 of this number and subtracted it from this number, it'll give me negative 2 minus negative 2. So naturally when we do that, this is going to become 0. But this last cell, it was a 0. What I'm getting is negative 2/3 of 12. I don't know why I'm doing all that. We just said it was negative 4. So we're going to double this and add it. Double this to negative 8. Negative 8 and add it to this. So I believe we're getting a negative 8 here at the end. And what is negative 2 in terms of negative 3? It's a lot like 2/3, right? Or think of maybe the opposite, the negative of this scale that you used. So I'm going to write a 2/3 here. And that should be it. You can certainly check your work. These are our two LU matrices. And if I do the top row times, the top row, it gives me back 312. Oh, you can't see it anymore, but certainly the top row gives me 312 back. But in the middle, if I do negative 1, 1, I get negative 3 plus 0, negative 3. 1 plus this gives me negative 2. And then negative 2 plus this gives me 10. So you can see it reproduces the second row. I'm just going to say LU equals M. 3 of these would give me 9. Plus 2/3 of this is still 0. Gives me a 9. Plus 1 of these gives me a 9. 3 of these plus 2/3 of these. So negative 3 plus negative 2 should be negative plus 1 of these gives me negative 5, which is that number. And then finally 6 plus 8 is 14. Minus 8 is 6, is that number. So that did work out for us. Yeah, so this is my L and my U and our LU factorization. Like I was muttering earlier, like you could do this, I don't know why you would. You could do this with 9 equations. You could do a system of equations where you just take x, y, z, and you you jot down what L times U would be if you had variables here, x, y, z, and like I'm saying, another method would be do this, and then over here we have variables, right? But these are zeros. Multiply them out and just set them equal to m, whatever your m is. But and there's nothing wrong with this. It's just not very. What I did was obviously faster. And there's other techniques as well. This isn't the only way to do it. I mean, this is not bad, right? Like a lot of this is there's a lot of zeros here, so it's not as bad as it looks, but I still don't want to do it. So for instance, one equation is the bottom left. The bottom left is YA equals 9. So we get a big system. I wonder how bad it really looks. Because the top is just 1, 0, 0 times this, right? So you get A equals 3. The top is just the top. It always is. So it's not as gory as I'm saying it is, but we get the more interesting ones. We get, so I guess it's not really 9 equations, is it? It's a lot of them cancel. But anyway, xa gives you -3, right? X times a plus 1 times 0 plus 0. And then x times b plus 1 times d. So xb plus d is second row, second column is this -2. And then xc plus e equals 10. And then ya equals 9. Yb plus zd equals plus 0. Yb plus zd equals -5. And then yc plus ze plus f equals 6. So you get 6 equations in this case, because the first row, I mean, you're always going to get n squared minus n, right? Equations to solve. But, you know, sad. No one wants to do that. I don't know how bad this would be, right? Like, solve for a, pop it in here. Yeah. Easier said than done, but... Oh, did I forget? I forgot. I do know A, B, and C, don't I? We do know A, B, C. I skipped the first 3 equations, so yeah, you do need to write those down. A equals 3, so you know also A equals 3, B equals -1, C equals 2. They're showing up, so you may as well replace those numbers. So that's not so bad. So we immediately know X. We immediately know Y. We don't know D yet. We'd have to plug it in here, but now that you've got X, you can get D from equation 2. You can pop it in here. Now you've got Z. So yeah, that's solved.